Okay, for this topic, 8-5, referenced in our Holt textbook, Chapter 7, Section 6, on page 495, you'll find a picture talking about how this topic is used. When we talk about dilation of similar polygons, you're talking about polygons that have the same shape, but they have a different size. You're going to need a ruler and some index cards. You may not find colored ones, but or even a piece of paper would probably work. But we're going to actually draw some dilations with this topic. Okay, the first thing you're going to want to do is to mark from every vertice in your drawing of this triangle ABC. They want to scale 2t, that's the point of dilation, a factor 3 times its size. So what you're wanting to do here is from point T, you're going to want to draw some lines. So watch carefully. You're going to connect T with A, and you're going to just draw a big long line. You're going to connect T with B. And notice I'm trying to use as much of the page as I can. Just draw your line as long as you can. So from that point perspective, we're going to do our dilation. So what we're looking at is AT, BT, and CT. So this is where your index cards come into play. After drawing these straight lines, we want to scale it 3 times larger. So to show this scale, I'm going to go to the center of dot A to the center of dot T and just make a mark. And we want that 3 times that size. So you're going to start from T and say there's 1, 2, 3. So from my T, if I need to show this, this is representative of 1 scale, 2 scale, and 3 times larger. So you're going from our vantage point T. If this is confusing, let's just back it up if you need to, but we'll look at it a few times. I guess I'll just use the same index card. You might want to mark that you're not using that one anymore. Okay, for AB, from the center of B to the center of T, make a mark. This is your first scale it by 1 time, it's that big. 2 times larger is going to be to here, and 3 times larger, notice I'm just moving my mark down and marking on the line that I had drawn from T. So again, if you need to show what this is the first one, this is the second one. You don't have to draw these lines. Mainly these marks are what you need. And this one's the third one. Alright, we've already used that one. So now I'll come around on this side of the card. From the center of T to the center of C, make a mark. That's 1 times larger. This would be 2 times larger. I'm marking this is 3 times larger. Again, you don't have to show these 1, 2s, and 3s. I'm just going to show it so that you can see where I came from with my scale. Alright, the main thing you want to show is the last marks, which was here, here, make them big and dark, and here. So our first triangle is ABC here, and if we scale it to make it 3 times larger, notice how huge it got. Again, draw your ruler to the scale of the 3, all the way out to the 3 times as big. So proportionately, if I were to enlarge this picture, that's how it's done. We're going to do another one. The dilation of this one is enlarged because it went from a small figure to a big figure. You use asterisks, and this will be shown in testing a lot. This went from A to A asterisk, B to the B asterisk, and then from a C to the C asterisk. So label your new triangle. It's 3 times larger. You enlarged it. A scale factor that's reduced, a reduction, would be a factor less than 1, like halving something, or a third, taking a third, and so on. So in this example, notice our point of dilation is on the inside. So from this dilation, again, you're going to take your T point and then draw long lines out from that point. And just make them, remember we're going to make the scale on this one is a 4 this time. So we got to make sure we make our lines long enough. So just use up most of this blank space that you have. It's a little off. Okay, another index card. For each one of these, you want to mark from the center to the center of the dot. There's 1. There would be, if you want to mark each one, 2. You actually have to mark each one just so that you can move up each time. And this is 4 times larger, so you're going from O to here, which would be O asterisk. And anyway, cross through each time you use one so that you don't use it again. T to M, marking it once, it's already there, twice, 3 times, 4 times. This is the point at which it's going to be M asterisk. Use that one. So measure T to L, slide, 2 times larger, 3 times larger, 4 times larger. Again, mathisfun.com has a pretty cool interactive program that you can actually look at things enlarged by a certain scale that you plug in yourself if you want to go and see how things become larger, and especially 4-dimensional objects. These are just 2-dimensional polygons that we're enlarging. When you get into 4-dimensional objects enlarging, it's astounding at how quickly the figure increases. Okay, connecting it, my new quadrilateral, this is a 4-sided polygon, becomes 4 times larger. So this would actually be the drawing of how much it changed. So if you think about it, it's not taking 4 of these figures. You know, I could probably fit 4 of them right here. 2, 3, 4. That's when you're talking about scale, you're modeling something getting either bigger and bigger and bigger, or smaller and smaller and smaller. So if you're looking at a pair of triangles and we want to tell if these are similar, notice all the tick marks for these. This is congruent to that. So this is considered an isosceles triangle, because that would also be 16. If this is 11, then this is also 11. And then they share an angle that shows congruent. These sides are the same and these sides are the same, then proportionately you're going to get the same proportion. So these are similar by side inclusive angle and then another side. So you can prove that JKL triangle is similar to MNP. And that is topic 8-5.